events of these things. And it's a delight today to introduce Dr. Marj Amini, who is an expert in ICP-MS, and we'll hear all about those things, but characterization and characterization of materials, specifically typically of sort of minerals, bioremediation, and a range of other applications, I believe. I'm going to let you take the floor and talk us through your activities. Just remember, of course, this is being recorded. We will have a Q&A session at the end, so please go ahead. Thank you.
Thank you very much, and thanks for having me here and letting me present the great, fascinating field of laser ablation ICP-MS. I hope I can convey a little bit of my enthusiasm and great respect for this technique today. So the whole concept of laser ablation ICP-MS is based on mass spectrometry, which is a very powerful tool in the analytical chemistry for elemental and also isotopic analysis. It has an extremely high versatility with having here ion source, a mass analyzer, and detection system. All three components can vary significantly according to the application that you need to provide high precision elemental chemical analysis, elemental as well as isotope. It has a very high sensitivity, and it covers a wide range of masses and hence elements and isotopes. And this is especially true with the ion source here is a plasma, which has such a high temperatures that it basically overcomes any ionization energy and can ionize and provide the ions for the mass spectrometer of almost every element from lithium to uranium. Now for ICP-MS, the sample commonly or ideally is in a liquid form. It's a solution that gets aspirated into the plasma and will then be redirected through the mass analyzer to the detection system. Now, if you have a rock samples, for instance, like us geologists, you have to undergo a lot of difficulties to get this rock into solution. It requires a lot of acids, harsh acid treatments. It requires a full lab infrastructure in order to make good use of the very great signal to noise property of a mass spectrometer. So, and also you will lose the spatial resolution, which a lot of us geologists are interested in. Now, you could kind of compromise with a micro drill, but there's only so much you can do with it. Again, because of the sensitivity, the signal to noise ratio, you don't want to lose that potential. So a wise man said, why don't we just connect a laser in front of the plasma and get rid of all the lab work and also gain the spatial resolution. So if you, for instance, have a precious rock like this meteorite, let alone an asteroid, and you want to directly analyze it without going to the whole effort of dissolving it, or you just don't want to deal with a lot of nasty acids or don't have the lab infrastructure for it and want to use simpler methods like fusion, for instance, then you could, just like us, you could take this meteorite and fuse it to something like a glass pearl or a glass bead, and you still get the bulk analysis of it in applying laser ablation ICP-MS with these tiny little craters consuming the sample. And you will get the data that are comparable to if you had actually done solution ICP-MS, which we did for quality control. Or if you had suffered through a good portion of your thesis, just like me, in picking little fragments, glass fragments of a whole rock powder, and just so you can discriminate between the two phases, then just to learn then afterwards that your lab will acquire a laser ICP-MS instrument, just of course just after you finished, and you could have done that with just one glass fragment, then you'll just learn, like me, a really bittersweet but really great appreciation for this technique. So the technique, I tried very hard, and I would really not say I'm an expert in it, so that's why I am just scratching all these areas. However, However, laser ICP-MS, and this is what I always say, laser ICP-MS never wants to work for you, it wants to work with you. So each one of these aspects are interrelated, and it's very hard to really strictly follow a procedure, which the laser doesn't follow really the procedure once you want to set up a method. So there will be a lot of back and forth, but I try to start with the general aspects and then leave you with some application notes as much as I can. But just please bear with me, it will be a lot of scattering. So the laser, and I don't think I have to say that, it is a very, unlike the laser ablation ICP-MS method, it's a very linear light. It is based on a very narrow spectrum, with a very parallel beam, which is in phase. The beam is in phase, and everything the laser can do, and everything the laser basically is actually written in the name. It's a light amplification by stimulated emission of radiation. Some said in former times there was debate to call it loser. It's anything but a loser. It's oscillation. They wanted to replace the amplification by oscillation. But I am very happy they didn't go through with it. And so just very briefly, for anyone who is not deeply into laser physics like me, it is the stimulated emission is basically based that an external energy source is activating or stimulating some like electrons in a certain medium to a higher energy level, to a higher unstable energy level. While the electrons fall back, they emit the light. So now the trick is to amplify that, and to amplify this effect, to emit it. I mean, this effect is well known as phosphorescence, fluorescence, but now the trick with the laser is that you have it intact. So with the so-called pumping or inverting the population, you will have all of the population of the electrons to really fall back and emit the light at this very same time. And that makes the laser beam so powerful. So technically, it was realized in the so-called laser head with an external energy source for the excitation, exciting a certain active medium or gain medium inside the laser cavity. And that is enclosed in between two mirrors, one of them being highly reflective and the other one being partially. So it lets a little bit of the laser light out. The other mirror, the other light, the laser light, is used to actually excite more to emit more of the light. And with a little bit of technical tricks, you can make this laser, the continuous beam of the laser, as a pulsing laser. You have little pulses of laser. With the pulse duration can be really determined. It's very short. Here in the nanosecond, our laser instruments, for instance, at EOAS have a nanosecond range pulse duration, which is very important later on that you see during the ablation process. So the laser, the active medium will determine the wavelength, and the pulsation will determine the operating mode. And so by that, there is a lot of lasers out there. They all differ from gas sources to solid state sources. It really depends on the active medium. For instance, there are ruby lasers, or the very popular neodymium YAG lasers, standing for neodymium yttrium aluminum garnet laser, where the active medium is that crystal, or the very common in earth sciences, the very common argon fluorine eczema laser. Both of them, unlike the illustration shows, both of them can produce a laser light in the range with a wavelength in the UV range of 193 nanometers. And you will see in a minute why that is important for laser ablation ICP-MS. So the laser ablation process itself, it's basically nothing that the laser light interacts with the matter, your sample, and a carrier gas will transport mobilize the excavated material to the ICP-MS. So there is a lot more to it, and especially during that moment when the laser light actually interacts with the sample material, whether it is a rock or a tissue or any sample that you want to analyze by ICP-MS. The minute the laser light interacts with the material, there is absorption going on. The energy from the laser will be transferred partially to heat. Melting can happen depending on your sample consistency. Vaporization will happen, and the sample material will be excavated. So what all of these processes is very, very broadly, basically, I don't want to say exactly, but broadly described by one physical parameter. It's called the energy density on the sample surface, or also called fluence. So what really the difference is between the lasers is you have a continuous wave lasers. That means there is no pulsing. The laser is a continuous wave. It does not appear in small pulses. What happens is that the laser continuously heats up the material. So most of the energy of the laser is transferred to heat, which can lead to melting and to effects that you actually do not want. What you want is you want to use the laser, the energy of the laser, to be used as a shock wave to actually expel the material out of it. And the shorter the pulses of your laser, the better is this effect. Because if you don't do that, you will get something like that. This is a crater that was produced by a very long pulsed laser, and in a rock, in a silicate rock. And this is called a destructive ablation or a catastrophic ablation. You also do not want any melt rims to form or melt droplets to fall back down onto the sample material, because and you will see in a minute, because you want the material to go to the ICP to be analyzed and not to get lost, basically, for analysis. What you really want is use the laser as a little drill. And that's basically what it is. It's a very expensive little drill. And the finer the drill bit, the better, the sharper the crater, the more accurate and reproducible the excavated material will be. And this is for several reasons important. So the particle distribution in your excavated material, in the mobilized material above the sample surface, is extremely important for the ICP-MS part. And in this seminar, I mean, the title says laser ablation ICP-MS, but I'm not going to talk a lot about ICP-MS. It's a whole seminar of its own, and we're not going to open up that kind of. But the laser ablation, if anyone who's a little bit familiar with ICP-MS will immediately see the analogon between particle size distribution and nebulization. If you have a liquid in the conventional ICP-MS method, you have a liquid. That liquid needs to be in fine particles brought into the plasma. And the finer the particles, the smoother the signal will be, and the better your results. So this is exactly the same for the laser. The finer the particles, the more uniform the particle sizes, the better the response of the ICP-MS. Also, the penetration depth of the laser makes a huge difference, because you need to know how much material you're actually excavating. And this is different from laser to laser, depending on the wavelength, but also of the pulses, and also of the parameters that you set on your laser and on your laser ICP-MS system. There are several parameters that I'm not really specifically going into it. There are repetition rates. You can, on top of the pulsation of the internal pulsation of the laser, you can actually give it a certain frequency, and hence adjust it according to your sample. The softer the sample, or the more prone to melting, you can increase or reduce the heat effect of it. And so that's why we did some investigations with a surface profiler, and that's why, again, I appreciate the whole cluster, the idea of the cluster. At that time, we were desperately looking for a surface profiler here on campus. We did found one in the very ample. Unfortunately, it's a diamond tip, so it's a surface which we cannot have. We then approached an optical surface profiler, and this is the picture you get. We did several parameters with several spot sizes and in several materials, and investigated the ablation, the drill depth, the ablation rate, basically. Why is the ablation rate, or why, when I say you need to know how much material you actually excavate and release from your sample by the laser, why is that important? So you have your rock, And usually you just analyze a certain amount, put it into the ICP. Now the ICP spits out a signal that is usually a current, but it's basically, or counts per second, or a count, which is meaningless until you translate it to your desired physical parameter, concentration or isotope ratio. And you do that by the so-called calibration. A calibration is basically a conversion of a technical signal that a mass spectrometer gives to you to the desired parameter that you're after. And usually usually the way it's done, it's by comparing something very known that you know, a standard material, to your sample that you don't know. And by the very direct linear comparison, you can then relate to the analyte, to the desired analyte. So that is called external calibration. There is also an internal calibration. Along the process of whether it's laser ablation or liquid aspirate or solution ICP-MS or any other mass spectrometer, there will be some handling biases. And even within the ICP-MS, there will be drift, instrumental drift due to temperature changes, lab changes, the ICP-MS build up, sample build up, and that is called internal calibration. Now in laser ICP-MS, that is internal calibration is a little bit easier, and we work closely with other methods together. You need just one element that is the so-called internal element, and I will explain in a little bit more about that. What is difficult for laser ablation in ICP-MS compared to other mass spectrometer analysis is the so-called matrix matching. And again, this is a very broad field, also very applicable to solution ICP-MS, but especially severe for laser ablation. Matrix matching means that your standard, an ideal calibration, you would have a standard or a reference material that behaves exactly like your sample. Now for matrix, that is hardly impossible. That is hardly possible. But for laser ablation, it's especially impossible because you do not have the option like solution ICP-MS where you can actually spike your sample. You spike your standard into your sample, in the sample solution, and then run it, and then calculate it out as if done with standard addition or isotope dilution or double spiking. With laser ablation, you have a solid sample or any kind of sample, and then you have your standard. And that's where the drama, I want to say, begins. I will show you the severe effect of it. So it's very subtle. You may say, oh, well, I mean, I can use a calcium carbonate some sort of calcium carbonate to actually analyze my calcium carbonate samples. Now, this is a purely aragonetic calcium carbonate piece of a shell. And we analyzed across this line. And I don't know whether it's visible or not. It's very, very subtle. This is the so-called palea line. And this palea line is, nothing changes in the mineralogy, nothing changes even in the organic amount. It's just the microstructure changes a little bit. And we analyzed across that strontium isotopes by laser ablation ICP-MS. And you can see that across the transition, the ICP is anything but happy. So you will see the matrix effect immediately with subtle changes just with the microstructure. And this is very specific for laser ablation because the laser ablation is so picky, it's so fine that it actually really absorbs any changes in structure as well as chemistry, unlike solution ICP-MS. So there are a lot of, it's a whole research field who have focused or dedicated their lives to actually make standards, laser ablation standards. And there are synthetic standards, there are natural standards, there are glass standards that are fused to glass, natural and synthetics. For biological samples, for instance, they try to combine a lot of, like, let's say, muscle shells and make a powder pellet specifically for these kind of samples. And it is very challenging, especially it has to be used, even if not as standard, as a primary standard material, it has to be used as quality control material. And the whole production, it's a whole industry behind it. So what proved to be useful are the so-called reference material, certified reference material, like this NIST series. It is a series of fused synthetically soda-lime silicates. They have been spiked by specific amounts of trace elements gradually from 400 ppm to 40 ppm to even less. And they have been made sure that it's homogeneous. A very, very big requirement for standard materials is homogeneity, just because the laser can pick up everything. As I said, the laser is extremely vigilant about everything. Chemistry, structure. So, and because it has the spatial resolution, it will pick up every little defects or inconsistencies. And it has to be well characterized. So there are a lot of ring tests around the globe that share reference materials, newly referenced materials. They certify it, they characterize it and certify it. And obviously, like every standard material, it has to be available. And so once you have a good grip on your standard materials and your quality controls, then you can apply the very classic scheme of calibration. You have your primary standards for the external calibration. In laser ablation ICP-MS, you have no choice but to do standard sample bracketing. That is, you analyze your sample, then you analyze, you start with your standard, then you analyze your sample and you alternate that. So you can draw a very nice calibration line between the two of them. And then the internal standardization. So the internal standardization is, as I mentioned, it's an element in your sample that you have determined somehow otherwise than by laser ablation ICP-MS with an independent method, ideally a very exact method like probe. And then you take that as a reference within the actual run and normalize every other analyte that you use with it to that element. Now, with that, exactly like the primary standard, you assume that this element behaves similarly to your internal element during ablation, during plasma, during the transport to the plasma, which is not always given, right? So it's an approximation. And this is shown by the very strong effect of downhole fractionation. So downhole fractionation is everybody is scared in laser ablation ICP-MS about that. It is a very simple effect that means that refractory elements, that is, they're elements with kind of a high condensation temperature, they tend to stick around the crater walls, or they tend to be sluggisher than the volatile elements with a lower condensation temperature that prefers to escape. And this is the more severe, the deeper the laser drills into it. So you can see with that the ratios between uranium, thorium, between a refractory and a more refractory and a volatile and a refractory element will shift depending on where the laser beam is right now. And this is especially a problem in uranium-lead geochronology. That is a heavy user of laser ablation ICP-MS, where like geochronology in general uses the daughter-mother ratio as a clock, basically, and uranium-lead does that with the uranium-thorium-lead decay series. So in order for these ages to be more or less accurate, you need a very, very good grip on the uranium-lead ratio, which is a problem with because you will have downhole fractionation with a refractory and a very volatile element there. So what you do then is go back to your external calibration. You have to assume that the external calibration material is behaving exactly or very similar to your sample. But that requires that you're not only physically, like if you do uranium-lead geochronology in a zircon mineral, for instance, it's not done by using a zircon. You also have to make sure that the uranium-lead ratio in that standard zircon is very close to your sample. That means in H, they have to be close, because otherwise, if you try to date a 2 billion old zircon with a 1 billion old zircon, you will overcorrect it because that uranium lead ratio for that zircon is different. It's lighter, it's smaller than the one that you actually have. And this one, we had a whole master thesis, like actually extrapolating mathematically, trying to correct for it. And because it's impossible, like it's not only impossible, you have to find the right zircon with the right age, you have to certify it to be used as a primary standard, and then you use it for your standard. And so there are a lot going on in that field, and a lot of people are working on it. There is a combination between really empirical and mathematical corrections. And this is actually the I want to say Achilles heel of laser ablation ICP-MS, but that's the limitation, where the laser ICP-MS data for geochronology, for instance, have the error that is absolutely not comparable to an exact method, like using a thermal ionization mass spectrometer. That is an order of magnitude smaller in uncertainty than laser ablation ICP-MS can provide. However, having said that, to the laser's defense, the time and cost and the effort you put into these exact methods may compensate for the lack in uncertainty, or may not. It depends on. What is certain is that laser ablation ICP-MS is a really, really great tool in combination with other methods, and it saves the thermal ionization mass spectrometer a lot of time and money if you screen your samples beforehand with laser ICP-MS method. So back to the ablation now. Excavating the material is one thing, but now transporting the material to the ICP-MS is another thing. You have to transport it quantitatively. Whatever you excavate or mobilize by the laser has to go as it is to the ICP-MS in order to result in accurate data. And the plume over above your sample surface has to be uplifted very, very quickly, very, very quantitatively, and transported. And this is not a trivial thing. So the gas that transports this so-called carrier gas that transports it has to be inert. It should not react. You imagine that above the sample surface, there is a little plasma in itself. The laser creates a little plasma in itself. So any effect that you have in the big plasma, you will have during laser ablation. So any reaction, formation of oxides, any reaction can happen right there when you ablate the material. So you want to avoid that. The gas has to be inert, and it has to be extremely light. It has a very good thermal uplift, so you can remove the material very quickly. And this is shown by the two gases that are mostly used, argon and helium, which, by the way, makes the laser ablation, unfortunately, kind of expensive. You have to use a noble gas for that. So the argon already has a much, much, much bigger plume than the helium. And this is especially visible during by the deposits that you create. The argon as a carrier gas will create a huge blanket above the crater, which is an indication of that the material just redeposited back to the surface and was not carried forward to the ICP-MS. On top of that, the whole ablation characteristic shifts a little bit because the laser, the excavation out of the laser crater is different. And then there is the cell design. The laser ablation cell design was for a long time a limiting factor until the design of a so-called two-volume cell. So in a classic cell, in the first cell, it's a very square cell, so you can put your samples in, flush it with your carrier gas. People recognize that in every position of the cell, there is a difference in ablation characteristic due to turbulences, due to not favorable or favorable gas transport and gas streams. And then the two-volume cell was designed. And that one has a little funnel in the middle. It's a very, very small ablation chamber that is basically right on top of the ablation site. So the whole cell is still flushed by the carrier gas, but the actual transport, the carrier gas, the aerosol that you produce that goes to the ICP-MS happens in a very, very small volume. And it's a funnel shape so that the uplift is actually even more supported. And that was really a game changer for laser ablation ICP-MS, I want to say. So this is a very modern cell that we have. Obviously, it has to be big enough so you can have bigger samples and more samples in it. This is the cell that we have in our laser ablation ICP-MS, one of them at PCIGR. And this is the little funnel that I was talking about, where the actual ablation happens. This has also the big advantage that the washout between two sample runs, between analysis, is very fast. So you will not have carry over from one sample to the other. So these were the first laser ablation systems. That's how they looked like. And these are the modern ones. And these are the two that we have at PCIGR. They're both 193 nanometers and a pulse laser, argon fluorine. And if you happen to come to the Pacific Museum of the Earth, and in the lobby, you will see in that little window the laser ablation system residing. And if you're lucky, and I'm not lucky, we will have a service, and then you will see the panels open, and that is the laser beam path, basically. So here are a few specifics, just if anyone wants to go back and watch the slides and see whether this laser is actually suitable for their samples. This specific laser is a very powerful laser. It was actually designed for the military, and then repurposed, luckily, to something useful. And it is in the 20 nanoseconds. The pulse duration is in the 20 nanoseconds. It's, as I said, 193 nanometers. And the very important aspect of this laser is that the fluence, this energy density, can go up as high as 30 joules per square centimeter. Why is that important? Because if you have materials that do not have a cleavage, the laser has a hard time, especially bright materials like quartz, for instance. The laser has a really hard time to drill, and what it does, it just breaks it. It cannot drill, it just breaks it. And this laser is with a little bit of work is usable for that. So with this laser, we can connect it either to a little quadrupole ICP-MS and analyze trace elements, or we connect it to a magnetic sector field ICP-MS and analyze also lead isotope ratios, or we do it both together. So as I said, I do not want to mention too much about ICP-MS systems. However, I would like to point out a little bit on that one. It's this quadrupole ICP-MS system. Why? Because it's a single collector. That means you analyze your elements or analyte of interest sequentially. But the more important part is that it's a very fast scanning ICP-MS. And the fast scanning is based on the mass analyzer, which is in this case a quadrupole rather than a rather sluggish magnetic sector field. Although I have to say the new magnets are so fast right now with some technical tricks, lenses and stuff, they actually reach quadrupole scanning speeds. But in that case, the quadrupole is extremely fast. So the scanning occurs, or the mass separation occurs between four metal rods that have the opposite voltages. And so any ion or charged particle will be distracted in a spiral curve, and only the ones with the right mass to charge ratio will hit the detector, the others will get distracted. So why is it so important that the mass spectrometer, the ICP-MS, is fast scanning? That is because laser ICP-MS is a time-resolved method. That means that the laser does not care about the ICP-MS. It just fires and it collects information. And if the ICP-MS is not capable on keeping up, you will lose the information, and you get just averages of what you could have had. So the time-resolved signal. This is an example of actually the current run. It's just running. Hopefully, it's still running. And I just took a quick snapshot of it. These are zircon analysis on the quadrupole ICP-MS, and the one spot analysis is basically, it starts here with a gas blank, and then it starts, the laser keeps firing, you will have one spot analysis, and this is the time-resolved characteristics. So there are data collected while the laser is ablating, and here you can see a change in the phases. Ideally, if in a standard material you want to have the elements all going parallel down, the fact that I don't say peak, it's not a peak, it's a spot, it's a time-resolved spot analysis. The fact that the different elements listed below there are parallel is actually good. If they don't, then it indicates that there is a fractionation. In a homogeneous material, they should be parallel. In a not homogeneous material, you actually see it's real, and you actually see different phases. Now, with the phases here, for instance, this is the pre-ablation. The so-called, the first peak is the pre-ablation, where you shoot with a laser. You use it as a little cleaning tool. You clean up your surface, and then you start the actual analysis. And then you will have this the pattern while the laser drills deep, the analyte transport to the ICP-MS get diminished, so you lose a little bit of signal, and then the laser stops again. So you can actually, if you have a different phase, you can actually select which phase you want to look at and get the result, the concentration data or the isotope data for exactly that phase. So here is another layout. So this one was, let me go back. This one was the lead isotope. So you see that even for the lead isotopes, you will have irregularities, especially for the beginning, which could be still some surface contaminants, which could be any kind of that the laser didn't couple with the matter, the material properly. So you have weird particle distribution. That explains the little peak at the beginning, but you can just exclude that, eliminate that. What you need to do is, in a very strict protocol, you have to subtract the baseline. And that sounds trivial. And you say, well, the gas, it's helium. What should that be? What should there be anyway? But you have to be careful, because it's an ICP-MS. An ICP-MS, the Achilles heel of the ICP-MS is the interference, because it's a curse and a bliss. It can ionize everything, so it just produces everything. So if you see here, if you look here, the red line, this is 29, is silicon. There shouldn't be any silicon in a 5.0 bottle super high purity helium. But this is not helium, this is actually nitrogen interference on the 29 mass of silicon. So you have to do your due diligence and do this baseline subtraction properly. Then you can select whatever selection you feel comfortable with. A lot of people are very strict and select everything just to be statistically conform. And then you pick you pick your standard material, your primary standard materials. You select your secondary standard materials as a quality control, and then finish your calibration and get your concentration data. Everything sounds very easy, is actually not that difficult, except for that the laser, because one spot analysis is typically for, let's say, uranium lead geochronology with trace elements, or for lead isotope analysis about 1 minute, plus minus with a washout, depending on what sample material you have and how you want to design your project. But let's say 1 minute. So in 12 hours, you can collect a lot of data. And to go now and select your integrations for each one of these spots is very, very tedious. Luckily, there are software packages that do it for you. So this, I plotted here the total beam, which is basically a not really physical parameter. It's just the sum of every mass, but it's just for visualization purposes. It's actually quite good. And the green line is the average of the reference standard NIST 610 over the course of the whole session of these 12 hours. And you can see it's extremely stable. That's exactly what you want for your primary standard and for accurate results. However, so having said that, using software packages makes your life way easier. However, you have to do your due diligence. Like, this is kind of a little bit where I lose a lot of people on laser ICP-MS, because simply because philosophically I get it. you're so excited to finally get your data and make a good story out of it. And while for other methods, you do all the nasty and annoying work beforehand and then collect the data, even sometimes by the software and by the ICP-MS already reduced for you and calibrated, and they spit out the results for you. With laser ablation, the annoying part is afterwards. So if you have done that, though, you get rewarded with a lot of cool data. And this one was a project that was a PhD project at PCIGR. The PhD student, picked a lot of bones from the Skladina cave in Belgium here, and these mostly were cave bears. And what he wanted to do was trying to solve the question whether these bones are actually from that sedimentary layer or reworked. So he could use stratigraphy to actually to put a timestamp on the whole story around Skladina. And so what he did was taking these little bones, and we ablated them from outside to inwards, and then we could see actually for every element, trace elements, the diffusion profile and the sedimentary signal, and correlate that with the sedimentary layer. Was a very cool project. So the stability, just a little bit of the uncertainty, analytical uncertainties. This is a BCR2G reference material data over a couple of sessions. It's a dark basaltic glass, and a typical analytical uncertainty is around 10%. You can assume. Usually, it's way better within one analytical session, but in this case, it was a trace element uranium-lead geochrons session with zircons. So a long-term session, that one was from one of our PhD students who collected all of the BCR2 samples and all of the data along her PhD thesis. And this is over a couple of years, and this is basically the long-term stability for the mass spec. So once it's set up and nothing severe happens to especially the lab infrastructure, a laser ICP-MS system is a very, very stable technique. For the lead isotopes, it's a bit similar. We have the primary standard up there, and the primary standard, in this case, it's a little bit easier because you do not need an internal element. You use a lead, it's a radiogenic isotope system, so you use a fixed isotope ratio to normalize everything. However, for the lead isotope analysis, you can see how sensitive it is to any change in tune parameters. So we admix what we usually do for trace elements, a little bit of nitrogen to enhance the plasma temperature and the plasma intensity and stability. And you can see that the data for the uncorrected data for the primary standards really shifted downwards. And you can see that with shifting spot sizes, you get a lot of scatter. Lead isotopes it's extremely sensitive to the sensitivity. It really doesn't matter where it is as long as it's consistent for the primary standard, because you refer then your samples to that very value of it. This is the KL2G. It's also a dark basaltic glass, and it was calibrated by the BCR2 values. However, the KL2G having 2 ppm microgram per gram lead concentration, while the BCR2 having 11 microgram per gram. And this is, again, going back to what we discussed, matrix matching uranium lead, not only the sample structure and mineralogy and composition has to be similar to each other. This is very, very obvious with this diagram. That was one of our PhD students who analyzed a lot of different materials with the same primary standard for calibration. And as you can see how quickly the analytical uncertainty shifts with the lead concentration values. And it was a cool study. She could tease out the different lead isotopic compositions in the whole rock, being here with a very uniform whole rock analysis, but then with varying lead isotopic compositions in the varying minerals. So one word to the split analysis. When you split the laser beam and you want to, at the very same time, collect the trace elements on one mass spectrometer and the lead isotopic composition on the other mass spectrometer, you do compromise a little bit with sensitivity and accuracy, but not too much. Definitely not too much on the lead isotopes, because depending on your lead isotope composition, as we just saw, but more so with the trace element data. So this one was in one session that for a split session, and you could see when we compared to a single ICP-MS session, the sum of the trace element data, the analytical uncertainties suffered quite a bit. So one thing that I meant to mention is aliasing. And this is because I just recently learned about that and got super fascinated, because at the beginning I was very skeptical. I knew about that beforehand with because we are using this so-called squid. Aliasing basically means a periodic signal. And the periodic signal stems from the laser shooting in pulses. And I'm not talking about the internal pulse of nanoseconds. That is not registered by the ICP-MS, since the detectors have a dead time of in the nanosecond range. However, you pulse the laser yourself with a parameter that's called repetition rate, just to relax your substance. So when you do that, however, it could be, in very unfortunate cases, it could be that the ICP picks up on that. And then you get this jigsaw pattern of it's a very real pattern, because, and it's actually a good sign, because the ICP is so sensitive that it gets every little aerosol package that the laser releases goes into the ICP-MS. However, it's not favorable if you want to have in your paper a better analytical uncertainty. So the way to circumvent that is either, and that's what we have, you put a squid in between. That is basically, you split the tubing that comes out of the laser chamber into several tubings, and then you put them together. That will just mix it out. It's actually a bit sad, because you diminish the power of the laser, of laser ablation ICP-MS. Or you just extend the line from the laser to the ICP-MS and let, nature do its things and just time do its thing. Or the very elegant method, if you do not want to compromise and you want to use this very fast washout and you want to have the power of the laser, there's a very, very elegant method. Very recently, it's called the quad lock. It's done, it is installed on the ICP-MS, and what it does is it synchronizes the collection, the recording of the mass spectrometer with the laser. So while the quadrupole is collecting one mass, it's a single collector, as I mentioned, while it's collecting one mass with the other masses, the quad lock tells him exactly, okay, for uranium, you collect only at this point, and that will eliminate actually this periodicity. And this is very important for so-called imaging. For imaging, you usually have a line scan. The laser just shoots in, keeps going, and the ICP-MS collects data. But usually the pixel were very big in former times, because you just average over a long time. Now with the quad lock, or with these fast washouts that you have, you can collect a lot of in a very high resolution in a very short time. So in former times, before we installed the quad lock, this like 4 by what is it, a 4 by 10, 11 millimeters sized section would have taken us at least half a day, if not even longer. And even then, we would probably not have this sensitivity and this resolution, because we would have to scan faster. With this technique, that took us even not 2 hours. It was 1.5 hours or something. And another thing, you can see how light it is. It's the drill deep is less than 1 micrometers. It's extremely light, which is very great if you want to have a good idea about some sort of surface coating or any surface features. So this is something that maybe I just quickly browsed to it, and it's it's just an application that I just very much like because it puts a lot of methods together that help out each other. And again, laser-ICP-MS is a really, really great method in combination with other methods. This is a project where we worked on a mussel shell, on the hydrothermal, in the deep sea on hydrothermal vents. And it is composed by aragonite and calcite layers. And what we did was to actually determine the structure with the prismatic, the very classic prismatic layer and the very classic brick and mortar of the nacre layer. And the microprobe maps gave us really nice elemental maps. However, it reached its limits on a very small area here where we didn't know. Raman spectroscopies told us it's aragonite. It looks though very prismatic calcite. So we wanted to know what the chemistry tells us. And then what we did was using the laser, and the laser really revealed that it is a very weird layer. It's even not calcite. So we did trust in the Raman spectroscopy. We did some more resolution, like spot analysis, high resolution, and are working on that. What modification of calcium carbonate it is that has these weird partition coefficients. So I thought this is a very nice demonstration how probe and SEM and structural spectroscopy method can work together and reveal really cool things for the characterization. I would like to conclude actually with this slide that was a bit scary. Was my first steps with playing around with AI, and I gave him the title of my abstract, and it spit out the slide for me, which I thought, oh, that's neat. But then I saw this oxygen, and then I got really scared. Not because it's wrong, like ICP-MS cannot analyze oxygen because the ion source is under atmosphere, but because there is a method, it's a laser absorption. With that method, that method is specifically for oxygen. So I thought the scary part is not that AI can be as wrong as us, but it can get as confused as us. So thanks.
Thank you very much for a wonderful talk. Welcome questions, and anyone who's online also feel free to put questions. I am paying attention, hopefully.